Hello, class. We are talking today about linear modeling and covering section 9b. And the first thing you're going to see here on our slide is a linear model. We have 2 points, and you'll notice that the line changes at a constant rate. So you have a straight line, right? Along the x-axis, you have the independent variable values, and then along the y-axis, the dependent variable values. And you have a slope that occurs, whereas the change in the dependent variable divided by the change in the independent variable gives you the slope, or changes what the change is from point 1 to point 2, which is pretty cool. All right. The common, the linear model is the most common and versatile way of representing functions, and it's used with equations. And when we're evaluating things and trying to figure things out and look at relationships, the best way to do that is with the equation. So as you know, we talked last time about using tables and using graphs, and those are great, and they have their own uses, but in most cases, when we're using manipulations and modeling, we'll look at an equation, or we'll try to use an equation so that we can more easily manipulate mathematically the data. All right, it gives us greater power when we're creating and analyzing mathematical models, and therefore the linear functions are awesome in that regard. So if you look at this little picture here, this is what we call a rain gauge, and it's just gauging or counting how much rain is falling. So imagine that we measure the depth of rain accumulating in a rain gauge as the steady rain falls, and the rain stops after 6 hours. And we want to describe how the rain depth varied with time during the storm. So we want to say, well, it was so much per hour. You would have time as the independent variable, and then the rain depth would be the dependent variable. If we're dealing with a straight line, then we're dealing with a linear function. And in most cases, the rainfall here would be a linear function as long as the rain fell at a steady rate. Then we could use a linear function as a model to depict the rain depth at different times. And that would be cool. So basically, linear functions have a constant rate of change, and they become a straight line graph, as we saw earlier. The rate of change is equal to the slope of the graph. So we could say slope, we could say rate of change. We're talking about the same thing in both cases. The greater the rate of change, the steeper the slope. All right? And you can calculate that rate of change by finding the slope between any 2 points on the graph. So as long as you have the change in y, or the vertical change divided by the independent variable change, or the horizontal change, so vertical change divided by horizontal change, then we have the slope. Right? Remember, change too means distance, and it's a subtraction problem. So you have two values from like x to x, so 2 to 3. You would subtract them or find the difference, 3 minus 2, to get the change. That's what change is subtraction. All right, finding the slope of a line. To find the slope of a straight line, here's a picture again, you could look at any 2 points and then divide the change in the dependent variable by the change of the independent variable. The greater the rate of change, the steeper the graph. You can see that right there. All right? The smaller the rate of change, the shallower the graph. So that a shallow line, if you follow my arrow, would go not so far up, I guess, as time changes. As time is getting greater, then you would have a change of maybe 1/2, because you would go up 1 for every horizontal change of 2. So 1/2, where this would be 1. 1 is greater than 1/2, and therefore the graph is steeper for a line with a slope of 1 versus 1/2. Okay, so if you look at this graph, this is our first example. Describe the function, find the slope of the graph, and express it as a rate of change. Briefly discuss the conditions under which the linear function is a realistic model for the given situation. So we're going to go over to the paper here for a second. So here we have the graph. Now, what I would do is I would pick out 2 points. Okay, I would come up with the 2 points, and it's easier to find the coordinates on the axes. So I always, if I'm given that option, I always pick the axes. So this is 0 over, and then 700 up. and this point is 4 over and 0 up. So I come up with 2 points, and then I find their difference, or what the change is. So vertically, our change is 700 minus 0, and horizontally, our change is 4, let's see, 0 minus 4, to start with the same coordinate. So 700 minus 0, 0 minus 4. All right? And that's going to be 700 over negative 4, which is negative 175. And that's your rate of change, and it's in miles per hour. Okay? So it asks us to find the slope. We did that. We found it to be negative 175 miles per hour. All right, and that's you're expressing it as a rate of change. And then briefly discuss the conditions under which a linear function is a realistic model for the given situation. So what's happening here is time is passing, so time's getting greater, and the distance from home is moving up this way. But what's going on is our distance from home is 700 miles, and as time is increasing, our distance from home is getting smaller and smaller and smaller. So it looks like at this point, at 4 hours, we made it home because our distance from home is 0. So we started at 700 miles away from home, and 4 hours passed until we made it to home. Is that realistic? Maybe if you were riding in a train. I don't know what goes 175 miles per hour. Maybe an airplane, I don't know. Seem to be around 300 miles per hour if you're in an airplane. But it is realistic because as long as you're going at a constant rate, always 175 miles per hour, then it would be realistic. And possibly trains do that. I hope so. But it is linear, and it could be linear as long as your rate of change, your speed stays the same at all times. Okay, we're moving on to our next section. A small store sells fresh pineapples based on data for pineapple prices between $2 and $5. The store owners created a model in which a linear function is used to describe how the demand, the number of pineapples sold per day, varies with the price. So this is another one of those problems or situations where if the price is too small, then people aren't going to buy them because they think something's wrong with them. And if the price is too high, they're not going to buy them because it's too much money. But somewhere in the middle is a good max price, and you want to figure out what that is in order to increase your profits. So, example, the point, and you see it right there, $2 for 80 pineapples, means that at a price of $2 per pineapple, then for that day, you could count on selling 80 pineapples. And here we have $5. Notice the price went up to $5, and you can count on 50 pineapples being sold. All right? Now, if you have 100 pineapples, you're going to want to set your price at $2 so that you get them all sold. If you have 50 pineapples, then you would want to price your pineapples at $5, and that way you can sell them all, and you would earn more money in that case because you sold all the pineapples you had at a higher price. What is the rate of change for this function? Well, the rate of change then, you're going to notice if I take the difference between dollars, so that's going to be the horizontal change is $3. And then the price in pineapples, you start at 50 and you move up to 80 vertically. So it's 50 minus 80, which is negative 30. So to put that in a rate of change, you would have the change in the vertical change divided by the horizontal change, or the dependent change divided by the independent variable change. So negative 30 over 3 is negative 10. So the rate of change for this function is negative $10, and it's per dollar per price of the pineapples. So you would have negative 10, and then will it work? Or what's the validity of this model? As long as pineapples, it just means that every dollar that the price increases, the number of pineapples that you sell decreases by $10. And I would say it's probably pretty valid. The change in notice that the change in demand is negative because one is decreasing while one increases. So the increase in price, let's see if I can get both hands. The increase in price decreases the amount of pineapples sold, and that's why we have a negative rate of change, which happens. We have to make sure that our rate of change is modeled correctly. If it's a decrease, then it's negative. If it's an increase, it's positive. So be careful with that. It is valid for this model as long as the rate of change stays constant, which it will probably with each day. All right, and it also says under here, predict this change in demand for pineapples if the price increases by $3. Well, if it increases by $3, then you would take a $3 and multiply it by the rate of change, which is -10, and you would have -30 pineapples. And so that would mean that you would sell 30 less pineapples if you sold them at $3 more per pineapple, right? Cool. All right, rate of change. So the rate of change rule allows us to calculate the change in the dependent variable from the change in the independent variable. So you'll notice that we have the change in dependent variable is equal to the rate of change times the change in the independent variable. And that just comes from the slope. You know that the rate of change is equal to change in dependent divided by change of independent. So if you multiply both sides by the change in independent variable, then you have this nifty little formula here, and you'll use it on your homework. So I would make sure I know what it is. And we're going to go back to our image mate so that I can go through this example. All right, the water depth in a lake decreases at a rate of 11 inches per week because of evaporation. How much does the water depth change in 9 weeks and in 17 weeks? So if the water depth in the lake decreases at 11 inches per week, then we would say that's a -11 rate of change per week, right? And it's because of evaporation. The water is evaporating, and then the water goes down 11 inches in the lake. So a model for that, let's come up with a model for that. So water depth is going to be dependent, right? The water depth is equal to a -9 times the weeks. So the number of weeks is independent, and the water depth depends on the number of weeks that have passed. So that's our formula. So how much does it change in 9 weeks? We can use this, substitute 9 in for weeks, and come up with the water depth change, and then we can do the same for 17 weeks because it's asking for both. So in 9 weeks, what happens? We have the depth equal to -9 as our rate of change times 9 weeks, and that's going to be 81 inches less. So it'll decrease 81 inches, right? And I guess we can write inches there. That's going to be our new depth. And then if we have in 17 weeks, we can do the same, use the same formula. D is equal to -9 times 17. And that is going to be -187 inches. So it'll be -187 inches down after 17 weeks. So that's how you would come up with a formula and then use it to predict. Again, we're predicting what happens or what's going to happen in the future if the rate stays constant. So there we have it. Now I'm going to stop because we're around the stopping point, and then we'll continue on with the next section, part 2. So go ahead and stop this and watch the next one.